sir, I have posted in the group.
Okay, great. All right. So let's get started. Okay, I hope all of you can see my screen properly.
Yes.
Okay. All right. So in the last class, I introduced the BCS ground state trial wave function. And it looks like what you can see here. This is the VCS wave function. In general, UK and VK, these in general can be complex numbers. But right now we'll just take them to be real because we'll see later on that taking them to be real here does not really compromise any generality. So the place where we will have to really take them to be complex, I will come to it later. Okay, so what we now, if this has to be this, we also know that it does not conserve number. So this does not conserve number. Which means that if it has to be a good wave function, the expectation value of the number has to be very sharply peaked around its mean value. So let us try to calculate the expectation value of the number. You know that the number operator is given by this. Okay, now the advantage that we have here is that we are working with a system which is not spin polarized. So if you have equal number of upspin and downspin, the Cooper pair is actually a time reverse state. So therefore, I don't need to work with both the spins, though I could. So in principle, I can write it like this. Okay, I have written here k, I have written minus k. It does not matter because K is a dummy index and I am summing over K. So I could actually evaluate for this and evaluate for this. And if you want to convince yourself, you can go back and evaluate for both, but it will give me identical numbers because it's a non-polarized system. So I will make my life simpler and I will take this for only this particular case.
Sir,
Yeah.
sir, spin direction. What will be the spin direction?
What will be the spin direction? What does that mean? Spin.
Yes, yes. I mean, for the first notation, K up and K down is should be K up or
Tell me again, I'm not understanding what you're saying.
the first term you write C regard K up, then C K down.
Oh,
Is
sorry,
it
sorry.
K
Yeah,
down?
yeah. Sorry. Thank you. Yeah. Okay. So now this last step you have to remember because it is an unpolarized system. So that's the justification of this step.
Sir,
Yeah.
so what does this sigma index stand for?
Spin.
Okay.
Sigma index is always, oh, sorry.
Sir, in the
Here the sigma index will disappear.
okay, and in last.
And last one also.
Okay, thanks.
Yeah. All right. So this is the number operator. Now what I have to calculate is the expectation value of n, and that will be the G stands for ground state and BCS of course stands for BCS. Okay, this is what I have to evaluate. So let's go ahead and try to evaluate this. Okay, I take the summation outside. Then I have actually two products, and products of course I can take them together. So L and L prime. Let me know, write down first the full thing and then we'll see if it makes sense. So first is Psi BCS, the bra that I am working with, and then I will work with the cat. All right. Then I should have CK up, dagger, CK up. That's the number operator. And then I will have the ket, which is UL prime. Okay, actually, I am so far not really taking U and V to be real. I am taking a general complex number here, but it will not matter, as we will see. All right, and then this operated on 0. Okay, is it? And then there is a 2 here. Sorry, this I have forgotten, because this 2 is because I had twice of K up, CK up dagger, CK up. Okay, so now I have to evaluate this, and the best way to evaluate is, you see that this is a sum going over L, this is a sum going over L prime, and here I have this sum going over K. So this is not a sum, this is a product going over L, product going over L prime, and I have this sum going over K. So first what I will do is I will take all the terms with K separately. So I will take the term where I have L equals to L prime equals to K, that I will write it separately. So let me write down. Okay, and these will be multiplied by the remaining terms, because you see there was product here. I have just taken out the terms where L equals to K and L prime equals to K. That is what will go in the sum. The other will not go in the sum, so they will come out. 0. Okay, great. Is this okay with everyone? Let me actually change this a little bit. Let me put the 0 here so that it becomes more obvious. Okay. So far, so good with everyone. If it is so, then let me go ahead. So look again here carefully. What I have done is that I have taken from this one, I had this products of L going over all k values. I had L prime going over all k values. So I'm taking out L equals to k and L prime equals to k separately. I'm writing this first term. And then this actually here also there is a mistake. This should not be here. Rather, this should be outside. To start with. So this should be outside. Yeah. Okay. So I am taking the one where I have L prime equals to k, and the remaining factors in the product together they come here. All right. Now you have to recall what this 0 means. What was this 0? This 0 actually means that it's a vacuum state. It's a vacuum state for all k's. So actually, the advantage of second quantization is that since my anti-commutation takes care of Pauli exclusion principle, I can work with product wave function here. So in the first quantization, I had to use the full Slater determinant. Here I can use the product wave function. So at the wave function level, it's much more easy. So that's the advantage. So this actually is this. It is that every state with every k is empty. So it's a vacuum state for all k values. So now therefore, I can first evaluate, let me go back. I can first evaluate this part. This is the easy part. So when I take that factor, what should I evaluate? I have to evaluate this. Let me know if there is any mistake. Plus, then I will have VL star UL. and that will operate on the 0L state. So what is the value of this? Anyone who has already evaluated it? If not, let's go turn by turn. Take first the first term here. So this one is inner product of the 0 and 0L state. So therefore the first term will give me UL square. UL mod square. Okay. Then the second term, look at what I have. I have a creation here, another creation here. Now I am creating two electrons in this state, and I am trying to take the inner product of the state in which I have two electrons with the vacuum state. These states are orthogonal, so therefore this will be 0. Similarly, so whenever I don't conserve particle number, I will have to get a 0. Similarly, here of course I try to destroy on this vacuum state, so this one also will be 0. Now what will these be? This is the only non-trivial one. See, this is quite interesting to calculate, because what you have to do, as I told you, the only thing that we know how to calculate in second quantization is the number operator. So now what you do is that you can of course interchange these two. That will give you a number operator, so that will result in a minus sign. Then you can jump this one first here, so that will give you one minus sign, and then you can jump it again here. That will give you two minus signs. Is that right? So that will give you a plus sign, yes. And then you can again jump it here, and that will give you three minus sign. So you see, you get one minus sign from here, then you get one minus sign here, multiplied by one minus sign here, multiplied by one minus sign here. So the total number of minus sign is 4, so it becomes 1. And what you get at the end is Cl up dagger, Cl up, and C minus L down dagger, C minus L down. No, actually you don't get that. Do you get that? No, I don't think so. I don't think so. No, I don't go so far actually. Let me not do so much. This is going to make it even more complicated. So actually what I will do is, let me not by the way, when I told that I can interchange these two, is that correct? Actually, I cannot interchange these two, because if I interchange these two, then I will have a 1 minus something. All right. So actually, one step that I said was wrong. But so what we will get is, let me not interchange these two then. I don't interchange these.
So Pratap,
Yeah.
hi. So is it possible that we actually take these two fermion operators and assign them some meaning of an order parameter? and then in a mean field like description.
Oh, no, yeah, we can argue in many ways like that,
Mhm.
but
In that case, we don't have to really handle 4 fermion term.
yeah, but no, you can sometimes do it, but not always do it, because as you have seen that these Cooper pair creation and annihilation operators, they are not really bosons or fermions, so they have complicated relationship. If you take the complicated relationship into account, you can do it, but it will not make it much easier, because you have remember that the commutation of the Cooper pair operator was 1 minus n k up minus n k down. That's rather complicated to handle. You can do it with that also. But I'll show you here. So here, what I'm doing is I'm taking these two. So these two jumps I'm doing the way I explained. So that will give me 2 minus sign. So it will be a plus sign. Then C minus L down. C minus L down dagger. And then I have CL up dagger and CL up dagger here. So this is what? This is 1 minus number operator and 1 minus number operator of L up. So these, when I am taking the expectation value between the vacuum state, the number operator expectation values will always be 0 because this is vacuum state. But I have this 1 and 1 here. So this term will just give me 1. So this term again is 1. So I get UL squared plus VL squared, which is just 1. Anyone who has not followed the argument here, because right now I am doing this in longhand because we are starting. Very soon I will just be using hand waving arguments. For example, here we create 2 electrons and we destroy them in the opposite order. So therefore I know that it is 1. But in the beginning, you have to do it longhand so that you know how it comes. All right. So if there is no interruption from anyone, I assume that everyone agrees. So now let me take here the first term, which is the more difficult term. This term over here. This term is actually the difficult term that I will have to deal with. So this term, if I should actually write it, because so this term, what it will have is this, then I will have sum over k and then finally I will have uk plus dk ck up dagger c minus k down dagger, and this is over the k state. Actually, again, I am making a mistake here. This sum has to go outside because this is because there is a K here. All right. So now, what are the kind of terms that I have? Again, let us inspect the terms. I have, let's say, cross terms, which are like this one. UK star, CK up, dagger, CK up, and then I have VK, and then CK up dagger, C minus K down dagger. Now, if you take these kind of terms, the cross terms, you see that they don't conserve numbers. So let me write one of them, let's say. UK up dagger, then I have CK up dagger, CK up, then VK, so that VK I take it here, and CK up dagger, C minus K down dagger. Okay, now here immediately you see that you are creating 3 particles and destroying 1 particle. So therefore you cannot conserve number, and such terms will always be 0. So similarly, if I go here, VK star, then I will have this term, C minus K dagger, CK up dagger. Then I have these 2, and then here, again I will have 3 destruction operator and 1 creation operator. So this cross term, that is the one which is between these 2, that cross term will also be 0. What do I have to now work with is the non-cross terms. So the first non-cross term is UK mod square, and then I have CK up dagger, CK up. Now this is number operator, and since what I am operating on is the vacuum state, so this also will be 0. All right. So what am I left with? I am left with the last non-cross term, which is VK mod square. So this one let us write down. VK mod square, C minus K down, C K up, then I have C K up dagger, C K up, and then finally I have C K up dagger, C minus K down dagger. Okay, I have to investigate what happens to this term. Any guess? No guess? Okay, so let's do longhand.
It's a product of 3 of 1 minus k. 3 1 minus k terms as product multiplicated with each other.
Let me go back and yes, tell me.
Yes, sir. The last k minus k down dagger can be shifted until the first term is up to the first. I can replace it as a second term. Okay.
Yeah.
So we have minus ck down and minus ck dagger, and all the other terms I can't replace it with each other, because k up k fourth and fifth term we can't shift with each other, and second and third term we can't shift with each other. We can push the sixth term to the second place, nothing else. And then all of the factors are like 1 minus
See,
1 minus nk.
okay, first thing that you notice here is that you have equal number of creation and destruction operator.
Yes,
So
sir,
when
that
you
I
have equal number of creation and destruction operator, you have to be careful, because equal number of creation and destruction operator already tells you that your term might not vanish. All right. Now what you can do is exactly what you said is correct. I can take this one and I can take this one and first take it here. Then I can actually, yeah, the indices are not the same. Then I can take it here.
I can push it up to second position.
Then I can take it here. Yeah, exactly. I can push it up to here.
Yeah.
Right? So when I'm pushing all the things up to there, that means what am I getting is C minus K down, C minus K down dagger. Then I will have CK
All the other terms
up.
are fixed. All the other terms are fixed. All the other terms has the similar structure.
All the other terms of similar structure, yes. So let's write them down anyway. CK up dagger, and then I have last one, which is again same CK up and CK up dagger. Okay, what is the expectation value of this on the vacuum state of K?
These all these have 1 minus nk type term. 1 minus nk up, 1 minus nk.
Exactly. So this is n minus k down. By the way, I cannot hear who is talking. Who is talking?
Sir Amit.
Amit. Okay, yeah. So this is, I cannot see that actually because I have to minimize the window. Right. Okay. So now this is the, I have to take the expectation value of this between this vacuum state, and this will be 1. All right. Because you have the term which is 1 into 1 into 1. That is the one that will survive. All the other will have number operator. And the number operator, the moment it operates on the vacuum state, will give me 0. So this last term is the only term that is surviving. Which means that this the expectation value of the number operator is sum over k vk mod square. Now if I tell you that all this calculation that I did was actually an exercise in futility, I did not have done it. I could have gotten the answer straight away. How? Tell me how you could have gotten this without doing any calculation, applying physical arguments. Because very soon I will not do so much calculation. I will use physical arguments to go ahead. Why
Sir,
is
n is
this
the average.
obvious?
N is the average of the electron, right? N is average number of electrons.
Yes.
So here the Bk square is the probability of the creation of Cooper pair, and we have 2 electrons in a Cooper pair.
Yeah, that is right. So remember the wave function. This is the VCS wave function. This is the probability amplitude that the K state has a Cooper pair. And this is the probability amplitude that the K state is empty. So that means Vk mod square is the probability. This is the probability of K state having 2 electrons, because one Cooper pair has 2 electrons. So that's how this 2 comes. And then Vk mod square is the probability that they are occupied. So 2 into Vk mod square is the average occupancy of that K state. So therefore the total number of electrons would be sum over K. So you get 2K sum over K Vk mod square. Alright. So all these things you could have just written it in one line from the physical interpretation of the BCS wave function. There was really no need to do all this calculation. Nevertheless, when you start, it's better to do the calculation. You can use these arguments for more complicated calculations. Okay, so we now know what is the N average, and now I have to calculate what is the fluctuation in N, because the fluctuation in N has to be smaller, much smaller than N in order for this to be a good wave function, even in the grand canonical ensemble. So therefore, I have to calculate this root mean square fluctuation. So this is not root mean square, this is the mean square fluctuation. So therefore, this is n square minus twice n average minus plus n average square so therefore this will give me expectation value of n square minus expectation value of n whole square. All right. So what you have to do, this you already know. Expectation value of n whole square is nothing but 4 summed over Vk mod square whole square. But this one you have to calculate, and this will be part of this week's assignment. And this is very easy. You have to calculate, you know that n operator was twice of Ck up dagger, Ck up. So therefore, n square would be this operated twice. So you can take the 2 away. So 4 you have to take the, sorry, this is n square operator, and you have to take this expectation value. Okay, this I will leave it for you guys to do it. This is an assignment, but I will write the final answer for n minus n average whole square. So this is the mean square fluctuation, and once you do your maths correctly, this will become UK mod square, VK mod square. All right. Now remember UK and VK, UK square plus VK square is equal to 1. So therefore UK and VK are both of the order of unity. Okay. So therefore these will be, these are all of the order of unity. So therefore you are summing over all K. So this will be, if you have n states in the band, then this is proportional to n. Means this is not proportional to, sorry, this is of the order of n. And similarly, here again, these UKs and VKs are of the order of unity. So this is also of the order of n, which means that the fluctuation is what? It's a root mean square divided by the mean. That's a relative fluctuation. And this will be root n by n, which means that this will go as 1 by root n. So as my number of states in the band is larger and larger, as I have many states in the band, this fluctuation will become smaller and smaller. So for a macroscopic system, this fluctuation is negligible. This fluctuation is not negligible only when you are working with, let's say, small number of electrons, which is a situation that happens on nanoparticles. But that is a situation that we will deal separately towards the end of the course, and where many interesting things come up. But as for bulk superconductors, which is what we are trying to deal now, this is a perfectly valid and good wave function because the fluctuation is small. Of course, it's a good guess wave function. So these are all answers. One will have to put this in the Hamiltonian to variationally minimize with taking UK and VK as the variational parameters and see whether we get a consistent result. So this is what we will be doing next. We have a wave function and we will take this wave function, plug it in the Hamiltonian and try to variationally minimize the energy and see what we get. So we will do that variational treatment in the next class. But in this class, we'll introduce now the BCS Hamiltonian. So we have not so far introduced the BCS Hamiltonian, and that's what we are going to worry about now. Okay, we have derived the general Hamiltonian of interacting particles, interacting pairwise particles. And the general Hamiltonian will look like this. This is the Hamiltonian that I will be writing with full generality. Often the Hamiltonian with full generality are nice to write down, but bad to work with. But it's good to start from here and then try to drop the flab and keep only the meat. Okay, so K, L, Q, So this is what we had done during derivation, but you have to also remember that I could have in principle spin-dependent scattering. So I'll also have the spin index, sigma and sigma prime. I can have a scattering potential, an interaction potential in general that depends on all of these.
Hello, sir.
Yes.
Sir, as you are writing the Hamiltonian, I have a doubt. You also written the Hamiltonian for the Cooper pair in the previous class, right?
Let me first finish the Hamiltonian and then I will answer your question. Yes, tell me now.
Yes, sir. As you have written an Hamiltonian in the previous class, H, and you have averaged it between the size, right?
I have written a Hamiltonian earlier. Where have I written a Hamiltonian?
In the previous class, sir.
In the previous?
In the previous class, in the previous class.
In the previous slide? No?
No, sir. In the previous class, when you are talking about the Cooper pair.
When I was talking about the Cooper pair, yeah, I had written a Hamiltonian, but that was a two-particle Hamiltonian. Now I am dealing with all the electrons that I have. Okay. My earlier Hamiltonian was just artificially, I had selected randomly two of the electrons. But if I have to really look at the entire solid, I cannot just look at two of the electrons. I have to look at all the electrons.
Okay.
Okay. So now from this, of course, this is a Hamiltonian that just looks good on paper. One cannot solve it. It's just too complicated. So we will keep only the ingredient that is useful for superconductivity. So first is we assume V, I'm not putting all these indices, V to be spin independent. So if we really think that we have the phonon-mediated superconductivity, the lattice vibration is what binding the Cooper pairs in the singlet state, then of course the lattice vibration does not really care on the spin of the electron. The lattice essentially responds to the charge of the electron, so we can safely assume this potential, this interaction potential to be spin independent. Then we are dealing with the superconducting state. So therefore, of course, here in this Hamiltonian, we have not kept any inelastic scattering term that will change energy. But more importantly, we need to only keep terms that have non-zero expectation value with respect to the BCS ground state. So if whatever term here gives me a zero expectation value with this, I can just drop it. It's not important as far as superconductivity is concerned, or at least this formulation that I am trying to make, the VCS formulation, because those terms will anyway drop out. So I will leave it for you as an exercise to show that only this kind of terms will remain in the interaction. All other kinds of terms, you take the expectation value with the VCS wave function, you will get 0. So VKL sorry. Can you see my screen still?
No, sir.
No, sir. No, sir.
You are not able to see. Okay, I have to share again. Can you see now?
Yes, sir.
Okay, good. Okay, only this term will remain. What does that mean? This term means that I am taking Q to be 0. So Q0 means there is no center of mass momentum of the initial two particles interacting and final two particles interacting. So I have taken Q to be 0. And remember, if you center of mass, when we did Cooper pair problem, we also took center of mass momentum to be 0. This is a perfectly valid thing to do if I don't have a current flowing. So initially we are deriving the properties without passing any current through the superconductor. So I have the center of mass momentum to be 0. Then I have only singlet states that are destroyed and that are again getting created in the singlet channel. Okay, so with this, my VCS Hamiltonian So this is the VCS Hamiltonian. I think the time is up. We will stop here, but let me tell you what we will be doing in the next class so that we can set the stage for it. What we will do is we will take the expectation value of the VCS Hamiltonian with respect to the VCS ground state wave function. However, remember that this wave function is specifically constructed to work in the grand canonical ensemble. The number is not conserved, but it is very sharply peaked. So I have to put here the chemical potential into number because I am working straight in the grand canonical ensemble. So this I am dropping the VCS superscript on this. You have this G means VCS ground state wave function. So I will have to calculate this expectation value. Now, of course, the chemical potential we know that for a metal, the chemical potential is Fermi energy. So therefore, this is rather easy because all that I will be doing is that I will be calculating the energy expectation value with respect to the Fermi energy. But then I have to do a variational calculation. So I will do a variational with respect to UK and VK. Set this to 0. And then from this, find the values of UK and VK. All right. So this is for the next class. I will stop here and questions.
Hello, sir.
Yes.
Could you please explain again this why center of mass momentum q taken to be 0?
Center of mass momentum is taken to be 0 because you don't have a current flowing. Consider a metal with no current flowing in the metal. For every electron with a momentum k, you have an electron with a momentum minus k.
Okay, means average momentum of electron will be 0.
Yeah. So
Thanks.
here for the center of mass, so were you there in the Cooper problem when you did the Cooper problem? Because in the Cooper problem, we took exactly the same assumption. We took the center of mass momentum to be 0. If you put the center of mass momentum, you will get a higher energy state. The center of mass momentum will give you a kinetic energy, which will be a higher energy state. All right.
Thank you, sir.
Any other
Sir,
question? Yeah.
can you please explain why this mean square fluctuation is proportional to n and is in the order of n?
Okay. Have you understood why this is proportional to n?
Yes, it says that this goes in the order of unit score.
Exactly. It's actually
VK
this
square.
is not proportional to. This is of the order of. See, that is because Vk. So this Vk mod square is of the order of unity. Because you know that UK mod square plus Vk mod square is 1. So probabilistically, Vk mod square would be somewhere in between 0 and 1. And when you sum over all the k states, okay, some of them will be empty, so Vk mod square will be 0. Some of them will be filled. Vk mod square will be 1. But it will be of the order of the number of k states. Now you go to the next one that I have not derived, but I have left for you guys to derive, is the mean square fluctuation is U4 into UK square Vk square. Now again here UK is of the order of unity, VK is of the order of unity. So therefore this quantity is of the order of unity. So therefore the sum would be of the order of the total number of k states. Now it does not matter on whether it is n or n half n or 1/3 n, it's of the order of. So it should not be, let's say, thousandth of n. That's the only difference.
Okay, sir. So that this order comes from this on the fact of this is summation over the state. So
Exactly.
somewhat, yes,
Yeah.
Oh,
Oh, yeah,
understood,
yeah,
yes.
yeah. Okay. Sorry, I didn't explain that. The order is coming from the summation. Yes. Okay. Other questions?
Sir, can I ask a question?
Yeah.
Sir, while we are doing the Cooper problem, there the existence of Fermi surface was very crucial.
Yes.
But in this case, we don't actually need the Fermi surface. So can you explain the difference between the?
No. See, of course, we need the Fermi surface. Absolutely. So, in fact, so far we have just constructed the wave function. We
Yes,
have
sir.
not solved the problem.
Yes.
So, when we solve the problem here, we are constructing the whole thing with a number fluctuation, and therefore we'll have to work with this BCS Hamiltonian minus mu of n, and the Fermi surface comes here.
Okay.
If this mu goes to 0, you will
Yes,
see
sir.
that it will not work anymore.
Okay. I got it, sir. Okay. Thank you, sir.
Yeah. Anything else? So that will actually come later on when you start solving it.
Okay. Yes, sir.
Anything else? Okay. If not, I will stop here. All of you are able to access the OneNote whiteboard. Anyone has any difficulty in accessing the OneNote whiteboard link that I am sharing? Okay. So if you are all able to access, that's very good. I'll continue with this. Okay. So let me stop here today and see you on Wednesday.